Welcome to our April edition of our Pigments 101 webinar series. We're happy to have you. This month we will do a part 2 effort on mica effect pigments. However, in this webinar we will take a look at, do a little deeper dive on how mica effect pigments are created and designed, and how they're used in color design formulations as well. So with that, we will go ahead and get started. As we've done before, this webinar will be recorded, and the recording link and PDF of the presentation will be shared with all of the participants of today's webinar. If you have a question, please feel free to enter that into the chat box, and I'll address those at the end of the presentation. Or if you are more comfortable, you can direct a question directly to me once you get the presentation. So with that, I'll go ahead and get started. Just a brief history of effect pigments. I'm not going to go through all of the details here, but I did want to highlight a few things that I've bolded in black. In approximately 1655, fish scales were used initially to get that pearlescent look in terms of in clothing and other items that started in Europe. It wasn't until about 1942 that the first US patent was achieved for creating a mica and TiO2 pearl effect pigment. Fast forward that until 1963, where DuPont had another patent for coating micas with metal oxides using a sulfate process. And then in 1970, this is when new substrates started to be incorporated into effect pigments, where the bismuth oxychloride started to gain some industrial relevance within the effect pigment community. In 1981, I'm sorry, Ford begun to use pearl pigments in their automotive finishes. And then the continuance of new substrates continued in 1995 with the addition of liquid crystal polymers and other multi-layer pigments that were being introduced into various applications. That continued in 1996 when synthetic mica was introduced. In 1999, alumina was introduced as another alternate substrate, followed in 2000 by silicon dioxide, and then in 2002, glass flakes were introduced into the marketplace, expanding the effect pigment base to be quite large. So why do we use effect pigments? Effect pigments let manufacturers develop their own very distinctive color and effect. We know that colors support the balancing act between function and aesthetics, technology, and art. We've always heard that some of the color formulation is a lovely balance between science and art in there. So this is what effect pigments do for us. We also know that customers, and we all are customers in one way or another, typically buy not only for purely rational reasons, but also with their heart. So they go for something that catches their eye and something that they like. And we know that studies have shown us that about 70% of buyers will opt for an effect color regardless of the color that they choose. A little bit about optics before we go on. So the pure mirror surface will reflect the light equally in there. However, then you go to the opposite where the surface is rough, and you will get a bunch of hills and valleys that then scatter the light in all different directions. And this is a bit about what the mica effect pigments will be looking like at each surface. So Snell's law of refraction tells us that as the light rays are passed through different indexes of refractions, the light will be bent. And the output of that light through that interface will depict what the eye will pick up. So as far as the mica effect pigments are created, I spoke about the index of refraction. So a mica platelet will have an index of refraction somewhere around 1.4 to 1.5. And then on top of that, we bring in a metal oxide on top of that, which will have a refractive index of 2.7 to 3.2, depending on the type of metal oxide that's used, and also the number of layers that might be used as well. So the light will have to pass through both of these differing index of refraction layers. So in this simplistic TiO2 iridescent type of mica, the light rays will come through the air, which is the first index of refraction. It will pass through the air TiO2 barrier, which is the second one in there. Then it will pass through the TiO2 mica barrier. It will go through the mica and then back out of the mica into the TiO2 and then back out of the TiO2 into the air. So it makes 5 different passes through different index of refractions before the transmitted light exits that particular particle. In addition, there's going to be a portion of the light that's going to be reflected at each of those interfaces as well. So not only does some light pass through and get bent by the different index of refractions, it also gets reflected at each of those indexes of refraction. So when you combine the individual particles that are the mica effect pigments, that each of those have all of those hills and valleys that I spoke about, which reflect in all different directions, combine that in a film where the orientation of each of those particles will be different. Ideally, we want them to lay flat and orient in that manner, but in reality, there's going to be some degree of shift in orientation. But each time that light passes through and gets reflected back by the individual particles, you can see then how the color and effect will come about in the actual film or part that the mica effect pigments are contained in. So as far as the coatings, the color itself is determined by the thickness of that particular metal oxide. So in terms of the interference colors, which are TiO2 is the metal oxide, the silver is going to be this thinnest TiO2 coating all the way up through green, which will have the thickest of coating. So the refractive index will pass through, and because the coating is thicker, it will bend the light differently to be able to create those colors. If the metal oxide is iron oxide, that creates the earth tone pigments, with the bronze having the thinnest iron oxide layer, through maroon and red being the thickest. And when you combine both TiO2 and iron oxide, that creates the gold in there. And so depending on how thick each of those layers are, determines how red the red shade will be on those gold micas. So in the first section webinar that we've done, we talked about the mica size, defining the sparkle brightness and coverage. So the finer the particle size, the less sparkle and brightness that you will get. However, you will get the best coverage or opacity from that mica. And then conversely, the larger or coarser the flake, the bigger the sparkle, the higher the brightness, but the poorer of hiding and coverage that you will get. And you can see these by example with the depictions that I have here on the screen, where the finest of the particles will be much more opaque, but less sparkle, all the way up to the larger ones that are have quite a large amount of sparkle, but are not very they do not hide very well in terms of opacity. So typically, the different particle sizes are combined to gather both of these properties in there. And we can even take the particle size to the extremes into the glitter size. Here we have a product that is up to 450 microns in size, so we get a big sparkle, but obviously the coverage is going to be a lot less, all the way up to the super glitter, where we take it to 750 or 700 microns, so that you get a big sparkle and you can really set off your color formulation as needed. Also, last time we talked about substrate type and how that defines the sparkle and chroma and of course cost. So a natural mica, because it is mined from the earth, it's always going to contain certain amounts of contamination depending on where the mines are located. And that contamination will impact the amount of chroma that can be developed in that mica. It will also have less sparkle because the edges are going to be less pronounced and more rounded. However, it's going to be at a lower cost point because of the natural status of it. And then contrast that with the synthetic types. Because they're synthetic, they are going to be cleaner in terms of their color in there, so that the metal oxide that's deposited on that can develop the most amount of chroma possible. They will also have more sparkle because the edges are much more clearly defined, as you can tell in the picture. However, that comes with a cost. So depending on how you want to balance out all of your properties with your color design needs, you may go one direction or the other in terms of the substrate choice. So a pearl is a fairly simple reaction where the mica is put in a slurry in a kettle in the presence of an alkali solution, and then the metal salt solution is added to that kettle. And then it's a matter of time and temperature to determine how thick of a metal oxide layer will proceed to generate the desired color. So very simplistic, however, there is a science to that, so I don't want to demean the actual chemistry and the processing parameters that are present in here, but it is always helpful to bring it down to a little bit of a more reasonable understanding. So in the full process, the mica comes in its raw form, and it's then ground to the appropriate size, and then further size classified to the appropriate size, average size, and size distribution that's required for that particular product. As I mentioned, then it gets coated in the reactor. It is then filtered and washed. It is dried, and then it goes into the kiln to convert the metal salt to the metal oxide. And then each of those batches are QC'd and blended to create the final lot, and it's then packaged. And to the left of your screen, you can see a TEM of a coated mica, so that you can see the layering of the individual metal oxides onto the substrate surface. to give a little detail on how we can control the processing and the types of testing that we do along the way. On the left-hand side, I've focused the steps on the mica itself. So we bring in the raw mica, as I mentioned, and grind that in a wet process and separate it to the appropriate size, and then further clean it up to remove any overly contaminated products via a settling process that we do. Once the mica is prepared, then it's added to the coating reactor, as I mentioned, with the salt and the metal salt and the alkali. And again, time and temperature are the key parameters for the product development. And we test the color along the way via a drawdown against a master standard to make sure that we are in the right place. And once that's approved, it gets filtered and washed, dried, and then calcined to the final product. And then at the very end, the QC takes place with the color and particle size distribution. And then on our cosmetic side, we also take a look, we also measure some of the heavy metal content and microbial counts that are required for that type of certification. So how do we develop a mica? And it's really, and this is a very important but very simplistic slide here, is it a true collaboration with our customer partners. We take all of the ideas, and many of you have talked with me, and I'm always a what if kind of a question person. So I always try to generate the ideas that where micas need to go in terms of the color and effect that people are interested in. And then we bring that back into our team and we hash out the details and what it would be required. The team in India is used to be now, and I always ask it, my favorite question is always prefaced by is, could we do this, or what if we did that? And I never expect an answer right away. I always go back and think about it. So we truly do want to have a collaboration with all of our customer partners and to be able to push the envelope as far as it needs to be pushed in here. And so that process is a multi-stage and typically a multi-year process where we start out with idea generation, move on to proof of concept stage, and then into test market stage where we bring ideas directly to our customers for their feedback and input before we do our final commercialization. To that end, it's a layered process, and so there are many options to be able to put together to be able to develop a new product. And so we start with a substrate. Is it going to be natural mica or a synthetic? How thick do we want to make that? We do have the ability to grind the substrate into different thicknesses, which can impact the final aesthetics of it. And what type of particle size and size distribution? We can tailor that to offer a certain look by that distribution. Then the choice of the layering metal oxides or other materials on the mica. Do we want to use TiO2? Do we want to use iron oxides? And what color iron oxide do we want to use? We've been working with adding CICPs and other organic pigments onto these layers as well. And then, as I mentioned earlier, what thickness do we want that to be? And then do we want to use single layers or multiple layers? So all of those lead up to many different color options that are available. And we continue to push those boundaries to explore what we can make via this process. And in some cases, if it's a multiple layer, we may need to add a layer in there, which I've identified as layer 3. which is a bonding agent. And that depends on what two layers are being added on there. So in some cases, we may need to help the bonding occur with an additional chemistry layer to be able to keep that color onto the surface and that it doesn't get removed. And then lastly, the last decision that we want to make is what, if any, treatment is required. Is it going to be for weather treatment? Is it going to be other physical property treatments that are needed in there, and what that chemistry and thickness might be? So a lot of different questions to ask and a lot of different options that are available to us when we develop a new mica pigment. Just some different examples of how this design approach has resulted in new products for us. So we have, over the last year and a half or so, introduced several new products, initially into the cosmetic area, but these are also able to cross over into industrial. And here we've spent a lot of time taking a look at the substrate design. And in this particular case, all of these examples are using a natural mica as a substrate, but we've created a process where we have been able to increase the chroma to equal that of synthetic micas. And on each case, the exhibit on the right-hand side is the new product, so that you can see the higher amount of chroma that we've achieved through this development. And these are being compared to their natural mica traditional counterparts on the left-hand side. And I mentioned that a lot of all these products can be crossed over to industrial. And the case in point, the middle one in the blue one has already done that. And I've used that in a number of color of the month designs that we've put together, and we've found a lot of interest in those areas by using these pigments in here. Next, I talked about the thickness of the metal oxide. The base metal oxide will depict the final color. So on the earth toned series, we start out with the bronze, increase the thickness, we go to the copper, and then increase that thickness a little bit more, and we go to a maroon. And if we did one more step, we would go into a red as well. So you can see how that thickness then changes the color in there. Now, if we add a second layer of black iron oxide to each one of these, and that layer is the same thickness in each case, we start out with a walnut, which is over the bronze, and then we move to the cherry, and then finally we move over to the red oak. And as I mentioned in an earlier slide, we do different phases in terms of our product development. So both the cherry and the red oak are in the test market phases, where we are introducing these to our customers to get their input, and before we decide which ones will move on to commercial production. And we're confident in this one because it follows the same process as our walnut, which is already a commercial product for us. Next, to continue that theme, where we take a look at both the substrate choice as well as the metal oxide layer design. Here we have two products that are also in the test market phase, and we're calling them granite. We wanted to achieve a salt and pepper look with the TiO2 and black iron oxide. And so with the two different types of substrate, we get a difference in the sparkle effect when the synthetic mica is used, a little softer effect when the natural mica is used. Now, you'll notice that these are rather large in their size, and that's unfortunate because we wanted to be able to keep that distinctive salt and pepper look. However, when we tried this approach on a smaller particle size, we were losing that individual salt and pepper look, and it just became a gray, which is not the look that we were trying to achieve. And our most recent commercial introduction is our Regal Blue. And here we've combined, it's a multi-layer mica with the blue iridescent as the base layer, followed by a black iron oxide. This combination provides a nice smoky but very opaque mica effect in here. So, and it also has a sort of a hint of a maroon on the off angles. We have two products. We have the NXR treated for the exterior coatings grade chrome-free treatment on it. And then the base layer, the base product is the industrial or plastics grade product in here, so that you can see in both cases, you start to see that little hint of maroon in some of the off angles and the sparkle effect. So this is one we've just recently reduced and we're introduced, and we've gotten some great feedback on this particular product. So earlier in the phase, I talked about our proof of concept stage. So this is the stage right before we take a product to the test market phase. Here we're taking a look at using CICPs as a second layer on a coating. And in this particular case, we have used the blue iridescent and placed on top of that a black CICP, black 28 on top of it. So you can see how the color changes from a sort of a red shade to the green shade, but also provides a unique color position as well. And part of that, and I will grace you with a little bit of a video here that I've pulled up. And well, it doesn't, let me just pull that up again, where I show the way the flop changes with respect. And so here on the left-hand side is the iridescent blue, the plain, if you will. And then the other three products are different levels of the black 28 on the surface. So in this case, you can see how the difference in there changes throughout the angles. So as I mentioned, this is in the proof of concept stage. So we are getting ready to bring that out to test market phase. And we've taken a look at this in coatings, as you can see from this video and these pictures. We've also looked at it in plastics, and it is a very unique look to it as well. So the final layer is the surface treatment, and we always decide, do we need to put a treatment on it as well? There's two different types. There's the surface treatment and encapsulation. Encapsulation, as the name implies, completely covers the full surface of the particle, whereas the surface treatment only modifies the surface, so that there might be unexposed or exposed areas that are left on the surface with a surface treatment. So depending on what the failure that we're trying to recover from is, will depict what type of treatment is required, whether that be the full encapsulation or if a surface treatment is adequate enough to fix the ill of that particular particle. So we use the surface treatment for a couple of different reasons, primarily to counteract the the metal oxide that's on the surface. We all know that TiO2 is photocatalytic in nature, and however, the iron oxide is stable with respect to UV radiation. So if we need to protect that surface. The TiO2 types of micas would require more specialized treatment than the iron oxide coated materials. And then otherwise, there's such a high aspect ratio with the mica effect pigments that they become hydrophilic in nature. So in some formulations, we want to prevent any kind of moisture from getting into the film or part that can result in delamination or other structural stresses that the mica may wick that moisture into the film. So the treatment will protect that with that wicking phenomena from happening. So I've brought some examples of surface treatments and how they interact with the physical mica itself in terms of weathering properties. All of these application is a powder coating formulation that we've created, and we're taking a look at some outdoor accelerated weathering in all cases. And in this particular slide, we're taking a look at the particle size impact of gloss retention and color retention of silver micas. So all of these are silvers, and what we've seen is that gloss retention is particularly impacted by the size of the silver mica, where the smallest micas have the most negative impact in terms of gloss retention versus the larger micas, which makes sense because there's so much more surface area for the same volume and weight of material that in the smaller one than the larger one. Color retention is pretty similar across the particle sizes. This comparison is taking a look at the chemistry and the amount of surface treatment that we've used on a very fine mica. This is a 1 to 15 silver mica that we're taking a look at. The green lines are the chrome-free type of surface treatment, whereas the blue lines are the chrome-containing surface treatment. And in this particular case, we are looking at the higher amounts of surface treatment do provide the long-term weatherability that you might be looking for in a fine mica product. And here we're taking a look at the base metal thickness impact. And in this case, we're still on the TiO2 metal oxides, where we're taking a look at silver and gold, which is the next up in thickness from silver, and a couple of different particle sizes. And again, like we saw earlier, the particle size has a strong thing to do with a strong impact on the gloss retention. The smaller the size, the worse the gloss retention is, and also the thicker the metal oxide is, the better the gloss retention is going to be. And similarly, the color retention is pretty similar between all of these sizes as well as colors. But gloss retention is definitely a strong impact property. Here we also look at the type of metal oxide that's used, where we're comparing in the same size category, the TiO2 silver, the iron oxide bronze, and the mixed metal oxide golds. In this particular case, in both cases, the color retention and the gloss retention of the iron oxide or the gold are much better than the silver by itself. So we can see that the impact of that photodegradation of TiO2 has on these mica effect pigments that the iron oxide does not have, and it protects even in the mixed metal oxide multi-layer golds. That iron oxide does protect the gloss retention and color retention. So the different types of surface treatments that are typically used on the plastic side is anti-yellowing, primarily for the silvers. As I mentioned, when an exterior application is required. We've already talked about the chrome containing and the chrome free for exterior coatings applications, but also we will also can put on silanes and other coupling agents to improve properties like dispersibility as well. So having a large toolbox of options in terms of surface treatments and encapsulations is a good tool to have so that we can appropriately solve the problem at hand. So surface treatment is either bonded, as I mentioned, with the AY, the anti-yellowing, the chrome containing, and the chrome free, or it can be, or they're non-bonded, where either melamine resin or a wax is used to coat the mica particle, primarily for plastics application to help improve extrusion rates and flow properties within the plastic matrix. So in summary, as far as surface treatments is concerned, pearl pigments do provide that unique aesthetic, but they may come with some undesirable effects in performance. So these surface treatments are then used to address those performance needs. There is no universal treatment for all applications. As I mentioned, we want to be able to match the treatment or encapsulation to that negative effect, so that we're designing the failure mode out of the system. There should be, when we do put on a treatment, there should be minimal or positive impacts on other properties. But if there is a negative impact, we want to be able to understand that as well, which then leads right back to my statement that there is no universal treatment for all applications. And lastly, there's always the opportunity for a custom solution to provide the most ultimate performance in there over the standard one-size-fits-all type compromise that might be out there. Of course, that takes into consideration, is it the appropriate business case and need for that particular property. So, as I mentioned early in the slide, and I brought back the same slide in here, is why do we use mica effect thickness when it comes to color design? And the keys here is they do provide a distinctive color effect, and we do know that customers are buying not only for rational reasons, but they also prefer an effect color. So using all of those attributes that we do know from various studies in the industry, designing color with micas is a key choice for getting your product, getting eyes on your product. So what I've shared here is we've been doing colors of the month for the last year or so, and I wanted to share those with you here because each of those contain different types of mica effect pigments to get that statement across in here. So in here we've got the something called Garnet Fire, where we're combining a red iron oxide mica with a pink or red iridescent TiO2 mica in a 2-to-1 ratio in these different applications. So it makes a nice, intense, deep red look to the application. Next is our electric blue, and here's where we first introduced the unique substrate micas that bring additional chroma over the standard natural mica, and so here we're combining that high chroma mica, larger particle size with a standard smaller natural mica in these particular color formulations. Comfort Crush was introduced next, and again, we're using that high chroma blue, larger particle size to give a little bit more sparkle to the coating, in combination with the red or pink iridescent to continue that purple theme as we've combined it with the red 122 and the blue 15-2 in this particular coating formulation. Aztec Gold. Here we've moved on to the to focus on the gold micas that we spoke about, which are the two metal oxide layer system. And here we're combining a larger one to create that that sparkle pop with a smaller one, and then we tone it down towards the greener side with the iridescent green mica as well. Our Tangy Orange is a pretty simplistic formulation that's really just highlighting that gold 10 to 60 micron mica here in this, and gives a nice soft gold highlight to this orange. In December, we focused on our Starry Silver, where we're combining a gray mica for that base gray color, and then highlighting it with two sizes of silver. We have a large mica silver in there to give that sparkle, and then a smaller equivalent mica to lighten up the gray. And in January, we started off the new year with a bang, literally. Here we moved the micas into the clear coat to give that extra level of pop. And in addition to bringing it into the clear coat, we've also increased the size. So we're using very large silvers, golds, and a bronze to give that extra pop into the coating. In February, we put together Lemon Zest, and in the plastics area, we really wanted to focus on a solvent yellow dye because it's extremely transparent in nature. And then we combined it with a simple gold iridescent mica to give that nice little pop of sparkle, as well as a softer gold color into that formulation. And in March, we also did a color in the plastic side, where we really are just toning down the silver mica with a red mica, the iron oxide. So it's a 95-5 ratio of the two micas, just to give that soft coral look to it. And then this month, we moved over to decorative coatings, where we've moved the mica to the surface again with a larger particle size silver mica in that decorative application that we did in the top coat to show that a little bit of pop, but a little bit of unique aesthetics to the decorative coating. So I'd be remiss if I didn't make mention of Sudarshan's stance against child labor. We have a very strict compliance measures that we hold all of our suppliers to. So we have a zero tolerance towards child labor. You can read more about it by following this link on our webpage. But suffice it to say that we are part of a consortium with our customer partners on the cosmetic side to make sure that we have a sustainable mica sourcing plan that is followed up with unscheduled audits. Again, if you're looking for more information, you can follow this link to our webpage. So next up is our CPC blues that we're going to follow up in more detail. That'll happen in May. Again, as we've done before, you'll see the invitation in the prior week. And then in June, we are going to shift gears a little bit and talk about dispersants and pigments and how they can work together or they cannot work together. So stay tuned for June for that topic in our June edition. And then lastly, I'm just one part of the North American team, and you feel free to reach out to any one of us for any questions that you might have. We're always here to help answer your questions or provide any needs that you might have. And at this point, I'd like to open it up to any questions that you might have. So feel free. I will escape out of this presentation mode and into to see if there's any questions. All right, is there, so I don't see any questions. I'll hang on for just a moment here. If you have any questions, please use the chat box. Okay, well, I don't see any questions coming through. So if you do have any questions, oh, there we go. So question came in, will receive a copy of presentation? Yes, you will receive a copy of presentation as well as the recording of this particular item and in there. And then another question comes in about replacing metals with micas and pearls. Is this a trend? And depending on the application, this might be something that people are looking for. In a lot of cases, especially in areas that they're trying to go to autonomous vehicles, aluminum pigments are notorious for interfering and not helping in the LiDAR and radar recognition. And so a lot of some conversion from metal pigments like aluminum pigments into micas is going that direction, so that the LiDAR and radar can better see the vehicle with a mica versus an aluminum. Okay, so there doesn't appear to be any more questions. Like I said, if you do have a question as you review the presentation, feel free to shoot me a note. I'd be happy to help. But I do want to thank you all for your time and participation in today's webinar. And we look forward to seeing you next month as we continue the series.